So today I'm going to be talking about work on Mercurial signatures for variable length messages. This is joint work with Anna Lisyanskaya. So the application we're interested in is delegatable anonymous credentials. A credential could be something like your passport or a driver's license. And suppose that Alice is going to receive a credential from some certification authority. This is a signature on her public key. And suppose that Alice is going to delegate her credential to Bob. Then she may sign his public key. If Bob then wants to delegate a credential to Carol, but he wants to be known to her under some equivalent but unlinkable public key, PK prime, then he needs a way to update his valid credential chain from the CA and Alice. So using a new type of signature scheme called a Mercurial signature, he can randomize his public key as well as Alice's and update those signatures accordingly. He then may sign Carol's public key, and her certificate will consist of the chain of these public keys and signatures. So now let's talk about Mercurial signatures. Mercurial signatures were inspired by Fuchsbauer et al., and they had the idea of, instead of signing a specific message, you would sign an equivalence class of messages. And what this means is that the sign algorithm takes as input some message M, here in green, but the verify algorithm takes as input a message M in blue here, which is equivalent to the original message. And correctness here means that the verification accepts this blue M, and that the blue M is equivalent to the original message M given as input to the sign algorithm. Now, security here means that the adversary outputs some forgery M star sigma star, and M star cannot be equivalent to any message that was given to the signing oracle. So for normal EUF-CMA, it can't be equal to any message that's queried, but here, because we're dealing with equivalence classes, M star can't be equivalent to any MI. Now, the construction in that paper considers messages which are vectors of group elements, and a message is considered to be equivalent if it's a scalar multiplication. So here we have an original message M, which is G to the A, G to the B, G to the C, and we just raise all the exponents to some random value mu, and these two messages are equivalent. Now, Mercurial signatures considers the case of randomizing the public key as well. So the sign algorithm takes as input this public key in red and the message in green, and the verification algorithm takes as input equivalent public key PK in purple and equivalent message M in blue. Correctness says that the verification must hold and those values must be equivalent. Now, for security, the adversary has the additional ability to output a forged public key PK star. This PK star must be equivalent to the challenge PK. And like before, the message M star has to be not equivalent to any message that's been queried. Now, some important properties for Mercurial signatures are message class hiding and public key class hiding. Message class hiding says that it should be hard to tell if two messages are in the same equivalence class. And public key class hiding says it should be hard to tell if two public keys are in the same equivalence class, even when given signatures under both of them. And this was the non-trivial extension, was proving public key class hiding. Now, another important property for our application is origin hiding. I mentioned that when Bob is issuing a credential to Carol, he needs to randomize his credential chain. So this occurs in two steps. First of all, he can randomize Alice's public key without knowing her secret key and update the signature to this sigma tilde. But we need that the transformed value should be distributed like a fresh signature under that equivalence class. Now, when Bob updates his public key to an equivalent but unlinkable PK prime, the transformed sigma prime should also be distributed like a fresh signature on that equivalence class. So the key takeaway here is that Mercurial signatures allow this transformation of a public key, message, and signature into an equivalent but unlinkable public key, message, and equally valid signature, sigma prime. Now we'll talk about our prior construction of Mercurial signatures, just to give some background. So the prior construction was based on bilinear groups. So you have a bilinear mapping, which takes as input two groups of prime order P and outputs a value in the target group, also of order P. Alice's public key consists of a vector of group elements of length L. Now, the value p hat here is a generator of G2, and the values xi and the exponent are Alice's secret key. Now, Bob's public key, which is the message being signed, is in the first group, and the generator here is P, and the exponents are the MIs. Note that the public key is of length L, and the message is also of length L. Now, the signature consists of 3 group elements, which span the 2 groups. And for our particular construction, we have a signature of 3 group elements, and the public keys can be of 2 group elements. So each link on a credential chain is represented by only 5 group elements. Now, in terms of updating the signatures, Alice can have a randomized public key, which is her original public key raised to some value rho. And when Bob updates his public key, it is his original public key raised to some value mu. And these signatures can be updated so that they validate under the new keys on the new messages. Our prior result is that we were able to build delegatable anonymous credentials from our new type of signature scheme. And this was the first direct construction of delegatable anonymous credentials. All prior constructions required prohibitively inefficient non-interactive zero-knowledge proofs, such as Grasa-High. So this doesn't require any complicated zero-knowledge proofs. And again, each link on the chain is represented by only 5 group elements. And we were able to prove this secure in the generic group model. So now moving to the content of this paper, the question is, why do we want variable length messages? So we consider a situation in which users have credentials under different certification authorities. So Alice could have a credential from the government. She could also have a credential from her employer. And we want to construct something that allows Alice to have the same underlying secret key under both CAs. So let's see what happens if we try to use our prior Mercurial signatures in order to achieve this. So Alice's public key is of length L, and consider what happens if she has some attributes. So this could be like an expiration date of her credential. So for simplicity, I'm going to assume that there's just a single attribute, but our signature allows any number of attributes. So again, her public key would be of length L, and then she has a single attribute. And then Bob's public key has to be of length L minus 1 because he has the single attribute. So Alice's public key of length L signs the full message, which is of length L. This means that Bob's public key is of length L minus 1. This also means that Alice's secret key is of length L and Bob's secret key is of length L minus 1, just the discrete logs. Now, if Bob has a credential under a different CA, let's say just for simplicity he's at the same level, then he can also issue a credential to Alice, and now she's at level 3. So what does this mean? Her secret key was of length L, but now it has to be of length L minus 2. So this is a contradiction, and this is why we can't use the prior scheme for these credentials issued under multiple authorities. Also, for a single authority, when I say that Alice can sign Bob's public key and attributes of length L minus 1, even though this is possible to construct, the proof of security in that paper actually does not allow this. All messages and public keys have to be of length L. So the question is, how do we construct Mercurial signatures to allow messages of any length? So a message is a vector of length n plus 1, and the first element here, g hat, is a generator of g1, and each of the other components is written base g hat. And the idea here is to break the message into n different messages. So these are n messages of length 5. The first element is a new base, and then the next 2 elements just indicate the index. The final element is the content from the message, the UIs. And then what's this H tilde? So this H tilde is what we call a glue element. And it glues together these n messages and the original message M in an unforgeable way. And critically, in order for the origin hiding property, this H tilde must be computed relative to the new base G tilde as a function of the entire equivalence class to which the message belongs. That means that no matter which message in the class is signed, the glue element's discrete log base G tilde is the same. So if M prime gets signed, then MI prime should be equivalent to MI for all I. Now, when we have these n messages mi, they are all of fixed length 5, so we can use our prior Mercurial signature scheme to sign each of them. Now, the question is how to build this glue element. And this is the main technical insight of this work. So again, I mentioned that the UIs are written base G hat, so the discrete logs are these little MIs. And we consider a polynomial in which the coefficients are the discrete log values. We also consider a secret point x hat, which is contained in the secret key of the signer, and we evaluate the polynomial at this secret point. So as a first step, the glue is computed like this. It's the base G hat raised to the polynomial evaluated at the secret point x hat. But we need some pseudo-randomness for our hiding properties. So we actually sample a random W and we create the new base element G tilde as G hat to the W, and the UI tildes are the original UIs from the message raised to the W. So now we have this new message base G tilde, which is M tilde. And finally, the glue element is computed using a secret random value Y, which is contained in the secret key. So we have H tilde is the product of the UI tildes, which again have the randomness W embedded, raised to the polynomial evaluated at x hat, and with this value Y. Note that a fresh W is sampled for each message for pseudo-randomness, whereas the same Y value is used for all messages. And finally, you output the message M tilde and the signature H tilde sigma. So here is what the public keys and messages look like. So Alice's public key is of length 10. There are 5 elements, which we'll see in a moment, are used to sign using the old scheme. And then these secret values, which are used to compute the glue, are embedded in the final 5 values. So we have the x hat embedded in the exponent, and this y1 and y2. Now, the glue is computed using a single value y, which is the product of these two values. This is an artifact of the proof of unforgeability. We require y to be separated into 2 values. And the message here is p to the mi's, and we have the glue element h tilde and n signatures sigma I. So we are able to sign the capital MI messages using the first part of Alice's key. So x1 through x5, we just use the prior scheme. And note that the public key is of length 10, but the message can be of any length. So it can incorporate any number of attributes, which is much more useful in applications. Now for this construction that I mentioned, we are able to achieve message class hiding and public key class hiding as is, but for unforgeability and origin hiding, we actually require some relaxations. So in particular, we require an interactive signing protocol. So instead of a signer taking as input a message M and just outputting a signature, there's actually an interaction between the signer and recipient. So this occurs in 3 steps. So in step 1, the receiver gives a zero knowledge proof of knowledge of the discrete logs of the message. So these are the MIs. In step 2, the signer computes the glue value H tilde and the signature. And then in step 3, the signer gives a zero knowledge proof that H tilde was computed correctly. And the reason for the 3rd step is that a dishonest signer might try to compute the glue element incorrectly in order to break the origin hiding property. So we require this zero knowledge proof so that origin hiding holds for all signers, not just honest signers. And the first step, where you prove the discrete log of the message, this is something that was introduced as a type of unforgeability called existential unforgeability against chosen open message attack, which was introduced by Fuchsbauer et al. And this requires that the recipient give a discrete log, a zero knowledge proof of the discrete logs of the message. And while our construction satisfies this weaker notion of unforgeability and origin hiding, for the purposes of our application, it's completely fine. So that's because for anonymous credentials, typically the recipient gives a proof of knowledge of her secret key. So this is exactly the MIs here. And so this EUFCO MA really comes for free. And then relaxing origin hiding to incorporate the zero knowledge proof adds an additional step, but it can be computed efficiently. So both of these zero knowledge proofs can be computed using just standard Sigma protocols on committed values. So again, these are all reasonable relaxations given the application that we're interested in. So just to sum up, our result is that we were able to construct Mercurial signatures for variable length messages for this particular equivalence relation. And we've proven them secure in the generic group model under the asymmetric bilinear decisional Diffie-Hellman assumption. And that's it. Thank you so much.